Thank you, Zold, for the introduction. Hopefully you guys can hear me fine. So thanks for inviting me over. My name is Ashwin. So I am part of the computer vision team at Magic Leap. And today I'm hoping to cover a little bit about what we do as a company and also what we do in the computer vision team at Magic Leap, and kind of talk about some of the challenges that we have in computer vision and what are the things that we are looking to address. And hopefully you'll get a sense of the things that we're working on as well as part of this work. So, I'll start with what is Magic Leap One. We are a startup based out of Plantation in Florida, but me and Pratik, who's sitting here, both of us are from the Sunnyvale office, and we are part of the computer vision team. And we released our first version of our product in August of last year. So that's the Magic Leap One. So I'll talk a little bit about what Magic Leap One is, and then go into what are the computer vision aspects of Magic Leap and what's coming next in terms of computer vision. So the talk as such, I'll focus it more on the computer vision side. So the Magic Leap One is this device that I have right here. So if you guys are interested, you can come by later and I can show you some of this as well. So what it has is it's a full-fledged device on its own. So it has a display. An augmented reality display. So what is augmented reality? It's essentially a way for you to interact with your environment, interact with scenes in your environment, and work with your environment. So it overlays physical content on top of the virtual content on top of your physical space. So it's different from a virtual reality headset. In a virtual reality headset, you don't see anything beyond your display. In an augmented reality or external reality headset, you see beyond your display and you are able to interact with content, interact with world, and your virtual content can also interact with your physical objects. So that's essentially what we do as a company. We build these headsets and we build the whole platform. So we build right from the optics to the device, to the hardware, to the software, and the whole computer vision stack. And all this runs on this processing system that we have. So a lot of challenges that you will see, and I'll try to allude them as I go through the talk, is all these computer vision needs to run in a very, like a phone-like processor. So you're thinking about something like that sits on your latest Samsung or Google phones or Apple phones. And all the computer vision that's running on the headset, like SLAM, your world reconstruction, and all of these have to run in a small headset. So the challenges there are immense, because now you might have, in academia, you might have looked at all these great work that's been published, but it also comes with a huge amount of compute, and it gives you the accuracy at the cost of compute. And here you will see that all the processing sits pretty much in this, what we call as a light pack. And getting all the processing done in this kind of form factor makes the whole problem more challenging. So what we have here is essentially 6 CPU cores. And this includes all the processing for computer vision and all the processing also for applications. So we have a huge bunch of applications on a Magic Leap device, and all the applications also run on this device, on this processor. So that makes it interesting also from a computer vision standpoint, and also how do you get these applications running on our processing unit. We also have a GPU, and we also support OpenGL ES 3.1. So a little bit about what we do. So these are some examples of, hopefully the video plays. So this is the kind of thing that you would experience with a Magic Leap device. So you see some amount of content, you can play with your physical space, you can create the video is extremely jittery, but you get a sense of the kind of work that we do here. So you can place virtual objects on top of your physical world. So here you see objects sitting on your chairs, sitting on your sofa sets, and interacting with your physical space. And you have these creatures also interacting with your virtual content. And those are the kind of applications you can build with a Magic Leap device. So, and we also have a control that we have with the Magic Leap device, which also helps you as a way to interact or provide input to your Magic Leap device. So these are different. So this gives you an understanding of how computer vision is important, because you need to be able to understand your world so that you're able to interact with it. And these are some of the other examples as well. So we have different kinds of games, different kinds of applications. And we are building more and more applications as we go along. So think about you are a doctor and you want to operate on your patient, and you're able to see the overlay, the X-ray of the patient overlaid on top of the patient, and you can use that in your operation procedure itself. So those are the kind of applications that we want to foster and enable, and that can be only possible if you are able to see a virtual content on top of a physical space. And you need to be able to interact with both of these to enable these applications. So what is spatial computing? So like I mentioned, so the difference between AR, VR, and XR, or what we call as spatial computing, is that in VR, your field of view is occluded. You don't see anything beyond your glasses. And in AR, you place a digital content up top of the world, but then there's no interaction. So here, we also add that layer of interaction. So the digital content also interacts with you. It understands you as a person, and the digital content also interacts with your environment, interacts with your physical space, and that's the kind of work that we are doing at Magic Leap. So we are building a spatial computing platform that will enable different kinds of digital and physical things to coexist together in the physical space. And I just want to give you a bit of history of how we all started. The company as such was started way back, almost 7-8 years back now. The first device is what we call as a beast. That's what you see here. So it's interesting to go back and see what are the kind of prototypes that we built before we actually came to this form factor. So what you see here is the actual display. That's kind of what you see in this. And so one of the things about augmented reality is that you want to be able to make it very easy for users. You don't want the users to experience fatigue over a period of time. And this display was the first display of the kind where we were able to show that you can watch a movie or watch some characters in virtual space without experiencing any discomfort. And that was this big device that we built back in 2013. And then over the years, we've transformed this device to what we see here. So, and along the way, we built multiple prototypes which look more like a helmet, which took it from the point of being completely non-portable to portable, and where you can experience and build prototypes and applications, which also test back to see what kind of accuracies do we need on the computer vision side. What are the challenges that we need to solve on the computer vision side? How are we going to address those challenges to make things better and to enable these kind of interactions? And so this is the working prototype. So this is around the time when I joined Magic Leap. I joined Magic Leap around 2015. And this is the kind of device I started working on when I joined Magic Leap. So here you see the whole sensor suite sitting on top of here, and the display, and the person can actually use this to create content, to play, to kind of see what are the accuracy, like what is the need from the computer vision side to solve this problem. And then now we are here. We released our first product in August of last year. So the main challenge, like I was mentioning earlier, is that you want to be able to solve this, what we call as a vergence accommodation conflict. So you have, typically when you see, you have your left eye and right eye trying to focus on this digital object. And this is the illusion of the object that you're creating in virtual space. Now, both the eyes are focused on this particular object, but then your actual display is right here. So your display is where the images are being overlaid. So now this is what the eyes are trying to accommodate and look at this scene, but this is where the eyes are actually focusing. So and this distance is what we call as a vergence accommodation conflict. And this becomes more annoying depending upon the distance of the object, and that makes it much more harder from a computer vision side. So Magic Leap was one of the first devices where we recognized that this is an important problem to solve. We have cameras looking at your eye, trying to track your eyes, to determine what is the distance that you're being focused at, and uses that to place augmentation at the right location. And that helps us make the device more comfortable, and you're able to wear it for much more longer periods of time. And so we have these 5 different things that we are focused on from Magic Leap. So I'll talk more about the contextual computing part, and that's where all the computer vision aspects of Magic Leap come under. So so these are the different, to build a device like this on an augmented reality space requires all these computer vision algorithms to work together. So we have a head pose, which is our SLAM solution. So as I move around in physical space, I want my content to stay in the same location. So I need to be able to track my location, and at the same time, I want to be able to, with respect to my environment, and that way I keep placing the content in the exact same location so that it appears as the content does not move. And that's what is head pose or our SLAM stack. And so then we have our eye gaze, I briefly talked about. So we have cameras looking into our eye, determining where to place the content to make it more useful for users. We have a control. It's a method of input to the device. So you can think of a V control, or we have a control here I can show later. It's a kind of a way to input algorithms to a device. And there are a lot of challenges here in terms of how do I do the sensor fusion algorithms and what kind of fusion algorithms I need to implement on the control to make it work and make it robust, make it accurate. And I want to be able to point with my control at a particular location and in the virtual space. So my accuracy of pointing to a large extent depends upon the accuracy of sensor fusion algorithms. And then I have hand gestures as a means of input to the device. So we support different kinds of hand gestures. So I want to be able to recognize my hands, and I want to be able to recognize my different key points on my hands so that I can create different kinds of hand gestures with that. We also have voice as a method of input, and we have an app on a phone where we can use it to provide input. And we can also have keyboards kinds of inputs to the device. So in addition to this, we also build a reconstruction of the world. So we can recognize that this is a flat surface, this is a floor, and use that information to also interact with the environment. So these are the four main components that I'll talk about in this talk. So the first one is tracking, localization, and mapping. So we build a map of the environment, and we track the user with respect to the map. We build the world reconstruction of the world, and track your eyes and place content based on the right locations, and also different kinds of hand gestures. And all these things need to run at the compute that I mentioned. So it all needs to run in this phone processor, and leaving all the remaining processing for all the applications as well. So you have very limited compute. And the challenge becomes, how do I get these computer vision algorithms to work with very high accuracy at the lowest compute possible? So this is something that's unique to AR applications, because unlike virtual reality, where you don't see your physical world, in augmented reality, you see your physical world. So if I place a chessboard on top of this table, and the chessboard does not stay on the table, and it's 1 centimeter above from the table, I would notice it immediately, because I go closer to the chessboard and I see that it's no longer sitting on top of the table. And if I'm playing a car racing game on this floor, I want the car to go on a smooth surface. So if there is a bump on this, I want the car to react to the bump. And all that involves very high accuracy and fidelity of my world reconstruction, my planes algorithm, and all that needs to be captured in the processing power that we have. So that becomes one of the main challenges for a lot of work that we are doing here. Starting first with SLAM. So a lot of people here, probably you guys are familiar with SLAM and what SLAM is. So it's a combination of tracking, mapping, and localization. So it's a simultaneous tracking and localization algorithm that runs on our device. So we map the environment, and we track the device with respect to the environment that you have mapped. So it's a kind of a chicken and egg problem, because you want to build a map, and you also want tracking as the map at the same time. So your accuracy of your tracking to a large extent depends on how well you're building the map. And your accuracy of your mapping depends on your tracking, because that's how you're creating points. That's how you're triangulating and creating points in your map. And map is important because you want to correct for drift. And there's always cases where your cameras are occluded and you lose track, or in a very low light that you lose track. Then you're looking at recovery algorithms, like how do I recover and come back and get back to my localized position. And then there is persistence that I'll talk about. So I want to be able to enable applications that are across sessions, across users, and how do I enable these kind of applications? So to give an example of Snap, so this is to give you an example of how our images from a camera look like. And you want to be able to use these kind of camera images to build the map and track the map. So here the user is going around this circular table, and we see our visualization, which captures how the user is moving around, and you see the map points that are being built, and the tracking with respect to those map points. So the accuracy and the fidelity of this is very important. So when you come back to the same location, I want to be able to see the same content in the same location. And that also means that I need to have very good loop closures, I need to have very good drift correction algorithms, and very tight fusion between camera information and inertial information to be able to achieve this kind of fidelity and this kind of accuracy. And at the same time, you want to do this at kind of keeping in mind memory and compute. So you don't want to build a very huge map because you don't have so much space on your device, and that also causes a lot of compute restrictions. So you want to have this trade-off where you're always looking at a trade-off between memory and compute and the algorithm accuracy. So that's kind of what you see also here. So it's more a sparse map, and that's the sparse map that we use for tracking as well. So we have tracking, mapping, and relocalization. So these are three fundamental blocks. So in tracking, a lot of tracking is based on feature extraction and matching features across multiple viewpoints. So to build this infrastructure, we provide a 6-DOF pose. So you start from this world point, you move the headset around, and you want to create a 6-DOF pose of the headset with respect to the world at all instants of time. And we also want it to be gravity aligned, because you want to have all these environments to be aligned to gravity and behave with respect to your world, your real world. And at the same time, you want to be able to track key points, track map points, and fuse vision and inertial information to be able to solve this problem. So while building this, we looked at several state-of-the-art approaches. You'll find approaches on both ends of the spectrum. So there are approaches which are, if you just take feature matching as an example, these are some of the state-of-the-art approaches that we have, right? And some of them are extremely high in terms of compute and provide very high accuracy. Others are very low in compute and also provide lower accuracy. So you want to find the gap in between, where you want to find a trade-off between very high accuracy and very wide baseline matching features. And at the same time, you want to find things that can actually fit in your compute and fit within your processing step. So to build this, we actually built our own proprietary feature detection algorithm, feature matching algorithm, and we built our own descriptor. And the descriptor is learned to support very wide baselines and work within our hardware constraints, our platform constraints, to be able to be accelerated so that I can finish the whole descriptor extraction in a few milliseconds. So that's the kind of challenge that we are looking at. So you want to have the end-to-end latency within the time frame of your camera, and I want to be able to build the extractor based on that.
You get published about pseudo-points, right?
Yes.
I guess that's not the proprietary descriptor then.
So that's the one that we published, yes. So SuperPoint is, I'll talk a bit of SuperPoint as well. So SuperPoint is, sorry. Good.
That also is a proprietary descriptor.
That's also a proprietary descriptor.
Yes. It's also a proprietary descriptor. But it's published.
Yes, it's published as well, yes. So SuperPoint is one example of a descriptor that we are working on, where we're trying to balance the trade-off between compute and accuracy. And the descriptor that we finally use is also another such descriptor, where we balance the trade-off between performance and accuracy. And that is very important for a lot of things. Like if you take examples like OpSLAM, SVO, DSO, or any of the state-of-the-art SLAM algorithms, several of them, there are direct and indirect methods. And if you look at the indirect methods like OpSLAM, they use OB as a feature descriptor. And they use 1,000 key points in a particular frame. And that just means the amount of compute that you need for doing the SLAM problem, right? So you need to extract 1,000 key points in a particular frame, create 1,000 descriptors, create all these map points, and track against the map points. That's the enormous amount of compute. So a lot of challenge that we are looking here is how can we reduce the number of key points? Can we do it with, say, 100 key points or even 50 key points? Can we reduce the amount of noise while selecting the key points so that the end of the process becomes much more efficient? So a lot of these are, the more you are able to optimize on the front end of your system, then it kind of goes towards the entire SLAM stack. So if the front end of the system is really optimized and is able to work well with as little information as possible, then you'll be able to make the whole thing work with as little compute as possible. So this is to give you an example of the kind of things that we optimized over. So we have, if you take feature matching as an example here, you want your descriptor to be variant to different kinds of noise. So noise comes with lighting variations. As you change the light in your environment, you have a different, the patches look different. And you want to be able to find a descriptor that's invariant to these kind of patches. You have different kinds of blurring. So if, as the user is moving, you'll be amazed how fast a human head can move. So in case some of the experiments that we did, we found that human motion can even move close to 500 degrees per second. So it can be an extremely fast jerking motion that can happen just in a very short period of time. And that causes extreme amount of blur on the cameras. And you want your descriptors to be able to handle those things. And how do I do matching across these kind of blur motions? And this also means that we need very tight fusion, because the only way we can handle extremely fast motions with noisy images and blurry images is through IMUs. And how do we integrate IMUs better to be able to solve this problem? And then we also have different kinds of rotations. So we have taking the original patch and rotating it by different kinds of orientations. You want your descriptors to be resilient to these kind of changes, so that I can do matching across multiple frames. So a lot of this involves learning the right descriptor to be able to handle these kinds of variations. And that becomes one of the core fundamental blocks in which our SLAM system is built on. So that's our tracking at a high level. On mapping, so a part of it is, so we rely a lot on stereo for mapping. So we have points coming from different frames, from different viewpoints, and we triangulate them to create the map points, and then create a sparse depth of the map point. And then we do a map refinement. So we, as the user moves around, we refine the map. We keep updating the location of the map so that we have a good representation of the map, and we correct for drift from time to time. So that's the core building blocks in which a lot of the localization and mapping algorithms work on. And now you need to start supporting different kinds of use cases. So what do I need to do if I want to go very large scale? What are the challenges there? What do I need to do if I have to support cases like multi-session use cases? So think of it that I want to play a game in my house, and I use a device on a particular Monday, and I turn off my device, come back the next week, and I want all the content to stay back in the exact same location. So during this time, your environment might have changed significantly. In this case, in this example, you just change the curtains, and that's it. So, but the environment looks pretty much very different. So you move around some pieces of furniture, change the curtain, change the carpet, but your algorithm, your SLAM system essentially is built upon these features. It's built upon localizing with respect to the map. It's built upon creating a map of your environment. And as an end user, people typically expect that, oh, it's the same living room and I want all the content back, and the content is not coming back. So it's very hard to explain to our end users and customers that your entire environment has changed and that's why it's not coming back. So from a computer vision problem, how do we solve it? How do we detect across sessions that I'm still in the same location and bring back the content in the exact same places that it's supposed to be? And how do I build my SLAM map in a way that's resilient to these kind of variations? So what are the algorithmic changes that I need to do for long-term localization and long-term mapping? So that's one of the challenges that we face, and this is something that we are working on right now. And the other kinds of use cases is multi-user use cases. So say you and I are playing a game together. We want to play a virtual chess game. We place a chess board on top of a table, and we are moving chess pieces. So I want to be able to I want to be able to see exactly what the other user is doing. I want to be able to, if he is moving a particular piece, I want to see the same piece moved on my side. So how do I enable these kind of applications in the SLAM system? So that goes to things like collaborative map building, placing multiple users in the same SLAM map and tracking them together and localizing them together. And how do I enable this kind of infrastructure? And obviously some of these problems also involve using the cloud. So not everything actually works only on the device. We build a map from one user, build a map from second user, pass the information to the cloud. The cloud constantly keeps updating the maps, merging the maps together so that both the users are in the same reference frame, same coordinate frame. And how do I do large-scale distributed map building? If I want to support a very large number of users in this particular room, like every single person here has a Magic Leap device. So then how do how do all of you collaborate together and build maps together? So these are large-scale problems that we are looking at, and at the same time keep the sparsity of the map so that I can run things on device and localize and track things on device. So going beyond that, so the way we expose this to end users and applications is what we call as is through what we call as the persistent coordinate frame. So what this does is it's an abstraction. So we essentially expose this to a developer and say that you attach content to what we call as a PCF or persistent coordinate frame. And at the platform level, we will make sure that the persistent coordinate frame does not move, and the developer just attaches content to the PCF, and the platform takes care to ensure that the PCF stays in the same location and across sessions, across users, and that way we can share content, share experiences, and across sessions and across users. So that is, so PCFs are auto-generated, they are saved with the map, and the content is all attached to the PCF. That makes it very easy from a developer perspective. We abstract the whole computer vision away from the developers, and that way developers are only focusing on how do I build content and enable multiplayer games, multiplayer experiences. And at the same time, on the computer vision side, we handle how these PCFs are managed. In a typical SLAM system, it goes through a huge number of variations in the map internally. Like for instance, as I move around, whatever drift that I have in the map gets corrected from time to time. So we update the PCF based on all the drift corrections. We try to keep maintaining the PCFs based on that. When we go in loops, we do loop closure. There are a lot of map changing events that happens all the time. And all the map changing events in turn result in changing the location of the PCF, and that's all taken care of by the platform, which is all abstracted away from developers, and the way the developers can still use it to build their own applications.
Good question.
Yeah.
So how much change is it resistant though? So your example that you showed is clearly not solvable. So suppose that is 100% and static is 0%, you know.
Yeah.
How much percent change are you able to tolerate?
So changes can be defined. So we need to quantify what changes mean. So a lot of work that we do is we build very large-scale data sets to quantify what change means. So change could mean changes in lighting. Like I come into this room is say 200 lux, I turn off all the lights and it comes to 20 lux, and that's one kind of a change. And then there is very large environment change where I move this whole one set of furniture out, but the remaining set of furniture is in the same place. And then there is also things like, in this example, your curtain changes or your pieces of furniture change. I'd say change the carpet here. So we quantify the performance of the algorithm across all these kinds of variations. So things like lighting variation are things that can be handled by the descriptor. So you have a better descriptor which is able to tolerate these kind of lighting changes. You'll be able to relocalize and get back the information together. So we do pretty well across lighting changes. For environment changes like this, if some pieces of furniture moving, it all depends on how much percentage of your scene has changed. So if it's like 70% of scene change, we can still manage it. If it's like 100% of scene change, it's hard to manage. If you're in a room where everything in the room has changed and all the furniture has moved around, that's going to hard to localize everything back. But as a computer vision developer, that's what they expect from a computer vision engineer. So they expect from the computer vision that this is my same living room, so I expect all the content to come back. Now, and regardless of what has changed in the environment. So that makes it harder and challenging from a computer vision side to see how do we manage these kind of variations. Yeah.
So you mentioned about sessions. So what happens if multiple users are trying to apply or move the same object at the same time? How do you handle that?
Interact with the same object at the same time. So it depends on interaction modality. So when we start, I'll show you some examples where it all depends on which pieces of object that I want to interact with and how I'm interacting with that object. Like chess game is one example where maybe you're working on different pieces of the object, right? And there could be like if there is a can or something else, it's a different kind of interaction. So we provide these functionalities to developers, and then the developer picks what kind of interaction model he wants to use for that particular object. So there are ways around, meaning that it depends on how, like, if you're interacting with your hand. So then we can detect with hands that that both hands are approaching or touching the object, and build that as part of our developer experience in terms of how the object needs to interact with both hands at the same time. Right. Any other questions? Yeah. Yeah. Right. So one aspect I'll talk about briefly towards the end is if I'm able to understand my environment, then I can even go one step further and say that this is the object which can move, right? Like your sofa sets can move or your doors can move in a particular fashion. So if I have a second level of understanding about my environment, moving beyond just sparse points, that will help me bridge that gap to the next extent. So it will say that these are the kinds of things that I can expect out of my environment. And these are the things that I can, which can move, which are things cannot move, and I can bake that in my information into my algorithm itself. I don't know if that directly answers your question, but that's the kind of approaches that would get us to the next step. Yeah.
No, but even as a human, you assume that you're entering the room again, and it's basically a perceptual problem, right? You don't know, the device does not know it has been there before. It's trying to find it has been there before. So if the room has changed completely and it looks different, even as a human, you would not know without prior knowledge that you were there. For you also, it's a new room. You are basically using some sort of a memory-based model to say, okay, I was there, and these objects are the same, but they look different. So
think of it the other way. So if you're in a hotel with a huge bunch of rooms next to each other, and every room has a different kind of, every room has the same layout. It has a TV in the same location, but everything else is different from every other room. So what is the expectation that you have? Like if you are, do you expect the content to come back to the same location in the same space, or each room is different, each one has a different sofa set, it has a different bed? Do you expect that the content should be different in each location? Yes, yes, yes. And the interactions with your objects can also change with respect to that. Like if I place a chessboard on top of this table, right? If the table moves, I don't want the chessboard hanging in midair. And I want the chessboard to move with the table. But if I place a TV on right next to, say, the door here, and I want, if the door moves, I probably want this TV to still stay there. So it also depends a lot on how developers want to interact with the environment. But as computer vision, we provide the functionalities and let developers pick what they want to do, right? So you have to have the ability to recognize these changes and bring back content. And how you bring back is part of the computer vision problem. And how developers use it and with respect to their environment is how they want to create their own experiences. Yeah. Yes. So that will be that's one of the directions that would help solve or address some of these problems, and also helps you identify give a better understanding about the environment. So eventually, you want your device to understand your environment really well and interact with the environment, and that's from a long-term perspective. That's kind of where each of these AR devices have to be. Right. Okay. So, so some of the other unique problems that we have with our device, our environments, is that so things like what we call as map selection. So map selection is, for example, I'm in the same location, I come back to the same location multiple times. Or I go to different parts of my room. So let's say I'm using my device in my room. On day 1, I use it in my living room, and day 2, I use it in my kitchen. And day 3, I walk from my living room to kitchen. So eventually, at the end of day 3, what I expect is I have one unified map of the environment which combines living room and kitchen. On day 1, I have only my living room, and day 2, I have only my kitchen. So when day 3, when I'm trying to bring back content, I need to pick which map do I need to choose to localize into so that I can get the content back. Now, that's something that is unique to us, to these kind of problems. When I'm looking at multi-session kind of use cases, how do I find out which map is more interesting for me based on my current location? And what map should I start using for my current experience? So that's one example of what we call as map selection. So we have to select the map and identify which map to use and start using that map for pose estimation and also for restoring all the content back. Restoring PCFs is essentially a way to restore the content back. So pose estimation is again with respect to the map that I choose, and then I restore all the content back, so now I know the content getting back.
How do you define where one map starts and another begins?
So it's all session by session basis, right? Because there is no definition of physical space. So it's all a sparse representation of the world. And the first session is map 1, and second session is map 2. And then that's where the map starts and ends, right?
But how are you going to assemble all the maps to build a computer vision of a large-scale magic verse?
Yes. So that is the goal. The goal is to be able to assimilate all this information together and merge them in a way that I build that information. And that's the challenging part. So it gets challenging as the number of maps grow. It gets challenging as the number of users grow. And the part of the computer vision problem or the challenge is to be able to get all this information together in a way that I can have one representation or a good representation of the world.
So I'll ask my second question.
Yeah.
You've been talking about how sometimes you use, the cloud to aggregate the information coming from different ML1.
Yeah.
But do you have a sense if, and I'm referring to compute.io, do you have a sense of at what point you're going to play more at the edge, local? So, I may have 5 ML1 in a room, they talk to each other, then go to the edge, then go to the cloud.
Yeah.
And how that will basically help to minimize the amount of back and forth.
So yeah, so the moment you start looking at cloud, there's also the compute and the cost associated with the cloud, right? And you want to minimize the amount of back and forth that goes from the device and cloud for multiple reasons. One is you want to use the cloud as less as possible. And second also is, but then if I am having an experience where you and I are in the same location, so the two, yeah, so either I have a framework where you and I talk to each other directly without going through the cloud, and then you and I are sharing processing, right? Where part of the merging happens in your device and part of the merging happens on my device, and then it becomes much more complicated to do. Or the other way to look at it is both our information goes to the cloud, and then the cloud does all the processing. So these are different kinds of architectural decisions that we have to take to enable these applications. And your user experience to a large extent depends also on these kind of decisions.
By the way, I like the question, but let's leave the open-ended one till the end.
Okay. So and then going forward to meshing. So meshing, I think I briefly talked about these. So this is to enable also things like visual occlusions. So I want to place, let's say I place a TV right here, and I'm using my device and looking at the TV, and a person comes in front of me, or in front of my Magic Leap device. Ideally, I want the person to occlude the TV That's when I know that the physical that's when it makes a realistic sense that your virtual content is occluded by physical content. That's your interaction with the virtual content. And so you want to be able to constantly keep meshing the environment so that I can identify these kind of objects and occlusions and place these virtual content behind your obstructions. And then there are physics-based interactions. You want your, like a video that I showed in the very beginning, you want your cars to go on a surface. You want your balls to bounce out of the objects in your physical world. So you want it to behave like a physical object in a physical world. And then there's environment sensing. So this is an example of our meshing algorithm in play. As the user moves around the environment, you can see that you're creating a dense 3D model of the environment. And this 3D model of the environment is then used for all these things. You want to, so these are the occlusions, and as the user goes around, you'll see all the occlusions getting filled up. And you create these kind of meshes of the world, which also helps you to simulate your physics in your real world. And then from this, we can go one step further and start looking at building planes, where you create once you have the meshes, you build the planes around these meshes, and that gives you the planar representation of the world. And different kinds of applications use different kinds of things. So you want your walls to be recognized as walls, and things to bounce out of your walls, and then their floors and ceilings and so on. So we talked about versions accommodation conflict. So I'll briefly talk about this video. So this is an example of our images coming from our eye cameras. So it's constantly looking at your eyes and determining, trying to triangulate the eye location so that I can place content in the right location. That helps you avoid the versions accommodation conflict. And this is something that's unique to a Magic Leap device because this is how we ensure that the user does not get fatigue wearing the device for prolonged periods of time. Okay. So this is an example of how we use it in practice. One way is to create applications and render it in the right locations. And the other way is also we have this application on a device called Avatar Chat. It's a social application. So you're creating your avatars and you want to interact with your avatars. So it's like, say, me and my friend trying to play this game. And you can see that the eyes of the avatar imitates what your friend is doing in the other side of the world. So that's essentially based on how your friend blinks and what the friend is looking, and all that gets simulated in your avatars so that you can get a more realistic view or realistic experience, or realistic social experience interacting with the avatars itself. So, so moving on to hand tracking. So we support different kinds of hand gestures as part of the system. It's a way to input content, select things, interact with your physical, with your objects. So things like open hand, close hand, OK sign. So these are kind of things that we support. We have a more key point based key point tracking. So we identify key points in your hands and then track those key points. And these key points are used for creating different kinds of gestures. And we classify gestures into different kinds of things. So these are the examples of the things that we want to classify. So it'll be more clear if we go through a particular video. So this is an example where I want to do a virtual hi-fi. So the two people can be literally in the opposite corners of the world. And I track the hands. So both the Magic Leap devices that both users wear track each other's hands so that I can create the virtual sense of giving a hi-fi in the world. So that's kind of I want to give you a sense of the kind of challenges that we have from a computer vision standpoint, working in an augmented reality space in a company like Magic Leap. So in terms of future, these are kind of problems that we are looking at. One is what we call as human-centered AI. Hopefully this video plays. Okay, I'm not able to get this video playing. But the idea here is that I want like a personalized assistant So you're used to your Siri or Google or OK Google answering your questions. So you want your personal assistant to do more. And it can be a physical person in space who's standing next to you and helping you in your daily tasks. So think of a physical, like a secretary, and that person is standing next to you and doing everything that you're saying. And the next thing that we also want to do is we want the person to imitate what a secretary would do or a person would do. Like you want this person to have the same kind of reactions, the same kind of facial expressions. So that it becomes more realistic. So you don't want a robot person standing next to you and expressing all these views. So you want a person to actually express things the way your friend would express things. So if you're sad, I want the person to be sad. If the person is, if you're saying something happy, I want this person to be happy. And that makes it more realistic, and it makes it more natural, integrated with your environment. So for this, we built our own platform to enable different kinds of facial expressions, scan different kinds of facial expressions, so that we can render them in real time, and the user can then use this for a secretary, which would be much more realistic. And there are many exciting projects that we are working on. I talked briefly about scene understanding and object recognition. So we want to be able to recognize objects in your environment, and so that we go to the next level of understanding from augmented reality space. So part of it include identifying what are chairs, books, or different kinds of objects in your environment, and how you interact with these objects. So that also gives me an interaction model. So there's a way that you interact with your chair, or a way that you interact with your book. And those things become interesting, both from an interaction perspective, from a developer perspective, and also from a computer vision perspective. Because you know that this is how your chairs can interact. Chairs cannot float in midair. So those things become very interesting as we start integrating them into our computer vision stack. And then there are things like object recognition and tracking. You want to be able to recognize and track objects. If I have this bottle, I want to be able to track this bottle as the bottle moves around in my environment. And maybe I want to place a content on top of this bottle, and I want the content to move as my bottle moves around. So that's again a different way of looking at the whole problem and interacting with the environment. And then there are a lot of challenges around multi-user that I briefly touched about. And some of the work that we are doing is purely classification in the 3-dimensional space, and some of it is more in the 2-dimensional space. We want to be able to recognize and create semantic segmentations of point clouds in 3D space, like in this example, and also create and recognize objects and place objects in 2D space. So think of an application layer. The user is trying to repair something in a factory setting. So I want to recognize, and there's an instruction manual that tells me, okay, move this piece of object from here to here. So I want my device to recognize that piece of object and as I'm moving that object, tracks that object and place it in the right location. So you want those kind of interaction modalities to be enabled in an augmented reality space. And there's a lot of these kind of applications and a lot of research topics that we are working on actively. So Magic SuperPoint is one such example. So here we have an example of our own proprietary algorithm for efficient feature matching that will again try to meet the compute constraints of our platform. So the challenges, like I was mentioning, a lot of challenges is also associated with what is the amount of things that I can do on device and a way that I can enable different kinds of these applications. I think that's kind of where we are, and yep, let me know if you have any questions. Thank you so much.
All have questions, so we can take some.
Yeah. So that is the way we want to approach it. So that's the kind of things that we can incorporate into our modeling, but that requires understanding of the environment and how the objects move and what kind of movement modalities it has. So that's the kind of learning that we need to do for enabling these kind of applications.
Does your platform allow developers to use their own compute power? Because I can imagine in some cases that portability isn't more important than, say, higher performing algorithms.
Our own computing power, meaning our
Like, instead of using your computer, use, like, say you have like 10 GPUs. Like,
so how do you connect it to the device?
could you do that?
Right now, no, but I mean, in future, it depends on how we want to go forward with it. Yeah.
Do you have a sense, it's kind of an open questions, as more and more ecosystems arise and try to tackle the shared maps of PCF, do you envision having multiple companies agreeing upon a single standard so that you can have a universal way to do PCF or universal map?
So I think that would eventually happen. There are some standard organizations that are coming up right now in the AR space trying to unify this representation. I think over a period of time, I think over the next 5 years, we would see that unification, I think, happening as well.
Thank you.
So with the chat app, when you have people in different maps, how do you resolve the different occlusions? Like if you're in a space this size and I'm in a small office, do you just click through walls?
So, I mean, you are working in your environment and the other person is working in his environment, right? So it could be that you are in one corner of the world and the other person is working on the other corner of the world, and each device builds its own map of your own environment, and then it's only about representing the unification of the space so that you can bring those interactions together. And so it's not so that becomes a way that where you place the avatar in your location and where the other person places the avatar in its location.
Okay.
Okay.
Thank the speaker again.
Thank you so much.